AGH Space Systems. So we are a part of a student engineering group that works under AGH, the University of Science and Technology. And our team is divided into three sections. So the first section is rocket section, and they do different kinds of rockets. Currently they are focusing on building fully liquid powered rockets. They are going to reach up to 10 kilometers altitude. They also have some experiments on board, scientific experiments, and to validate them, we use stratospheric balloons to put those experiments high up in the air. So currently, the experiment consists of testing how the shrimps, what are the so how shrimps react to being taken on a rocket, and are they viable to be used during interstellar travel. And finally, our section. So me with Shimon are from rover section, and we are focusing since I think 5 years on building Kalman. So this is our rover, it's in front of you, and I think we are missing a slide, right? Kalman is being built for different kinds of competitions. So the current state of Kalman is after 5 years of development. We have started from actually a different rover than Kalman. It was called Phobos, but we quickly moved to Kalman platform. And we are doing incremental features, incremental updates to Kalman. And after 5 years, we were able to finally win a competition in Kielce this year. And we have achieved first place in European Rover Challenge. So now I'm going to give a microphone to Shimon, and he will talk a bit more about different competitions.
Okay, thank you. So, as Miłosz said, competitions is a very important part of the development of our rover. There are plenty of them over the world. The most important one for us is University Rover Challenge. It's in Utah, in the United States, and it's the biggest competition. So we are very happy to compete with other teams there. Also, very interesting one is the European Rover Challenge. It's held here in Poland, in Kielce, and it's one of the biggest competitions in the world. So that's it. And yeah, each challenge focuses on Mars rovers and tasks that Mars rovers have to do. But there are some differences if we look closer into details. For example, in ERC, in European Rover Challenge, we are not allowed to use GPS, and it drastically changes how we deal with autonomous navigation and SLAM and things like that. And yeah, so we can move to the next slide. And there are a few photos from European Rover Challenge 2022. That's the competition which we were able to win. We got the first place, and we are very happy of it because that means that we are the best team in Europe. So yeah, it was in September 2022. Also, very important competition for us is URC. These photos has been taken a few months before, also in 2022. And we were the fourth team over the world, in the world during this competition. And by the way, the best team in Europe. Okay, a few words about our team. There were lots of iterations and discussions about the way our team works, and we are trying to constantly improve the development processes that we have in our team. And at the moment, it looks like that we got 4 main sections: the science, mechanics, electronics, and software. Each of them is responsible for developing new Mars rover ideas. We have also a project lead, which is Janek, and a system engineer, Cracow Robotics, which is responsible for he takes care of deadlines and dependencies between each of these things. And there's also a team development position, which is Adam Zagrajek, and he is a former project lead. And his role is to, because he was a project leader, he transited his knowledge to the other teams. And I've mentioned the knowledge transition, and I would like to talk a little bit more about it because there is a very big problem of generational exchange in student clubs. Because, for example, you have a company, it's no problem that somebody works for this company for about 10 or 20 years. But if it comes to student clubs, if somebody works for a student club for 3 years, it's a very long time because students graduate usually. So we put a lot of emphasis on that, on the knowledge transition, that the new the people that we recruit are able to continue our work. So yeah, that's it. Miłosz, Mike is yours.
Thank you. So before we talk how our rover is able to work, how it is able to operate, I would like to point out some key features that we have put to be able to complete the project. One of the main goals of our project is to be as modular as possible. And that's because if our rover is modular, we are able to adapt quickly to ever-changing tasks on different competitions. So we don't need to redesign entire rover from scratch. We only need to design a small part that is able to be iterated with the rest of the rover. Also, our rover needs to have some autonomy features that Shimon will be talking in a short while. Because on the different tasks, on different competitions, the rover needs to be fully autonomous. So we can't give it any control data, we can't interact with it in any way. I'm from electronics team, so my point of view will be more from that side. But actually, why do we need so much electronics in Kalman rover? So the first subsystem that is essential for our rover to be able to operate is a battery subsystem. So I don't think you see that, but after presentation you can take a look. On each side of Kalman we have 3 slots for batteries. And they are able to be hot swapped on the fly and are independent of each other. And in this way, we can quickly select if you want to have a more battery life or we want to have a lighter rover. And also, because of that hot swap feature, we are able to operate the rover like possibly 24/7. Next. System that I would say it's the first one in the class of student rovers is our suspension and drive system. We are using a slightly modified rocker budgie that you can see in the first picture. It works in the way that if a rover comes across some kind of rock, it will put up in the air the one wheel, and the opposing wheel on the opposing side will be pushed into the ground more powerfully, more strongly. And it is in that way the rover is way more stable. Also worth pointing out are the wheels, and they are able to rotate in 90 degrees to either side. And due to that, we are able to be rotating in one point. We can drive to the left, to the right, not like the regular car. Quickly, I would like to say how our rover is able to transmit data between different subsystems. So the heart of our rover is a master module. The master can be viewed as a router because it receives data from a ground station over RFA. And if that task needs autonomy, we can also connect PC, a regular x86 PC running a robot operating system, to the master module. And the master module later sends all of those data into the mini rack system. The mini rack system is a system that we have built during the last year, and its role is to route and do the commands that are sent from master module. And for example, one PCB that we have designed in that mini rack system is a motor controller. And motor controller job is to send data over the CAN bus to the wheels.
Why do you need this mini rack system between the master and, for example, drive, as they are on the same CAN net?
As I said before, we want to have as modular rover as possible, and it will be shown in a short while, but we have different boards that do different tasks, and master module only sends them the command to do that task. For example, we have a motor module that drives the wheels. We have analog marks that selects what video feed we get in the ground station, and so on. Yeah?
I think the question, how to say, the diagram is a bit misleading. Minirac is not between master and the other one. Minirac is actually containing all of it, right?
Not really, and I would like you to have. Okay, maybe different. I will talk about all those things in a short while, because I'm going to showcase the Meetup system. So if it comes to RF links that we use, the different ways of radio communication in our rover, the primary one is 70 centimeter band command and control. It is used in ground station to send commands to the rover and also receive telemetry from it. If we want to do some quick debugging, we can plug in Wi-Fi dongle that replaces the 70 centimeter link, and that is used to speed up the development and debug, because we don't need to put together all of the ground station components. One more addition from the last year that we have put in Kalman is the analog vision system. So Kalman has got different analog cameras all over its body, and using those analog cameras, the operators can have a real-time look through Kalman's eyes. And now I hope to answer your questions. Mini-rack standard that we have developed is a way to replace different PCBs that would be otherwise in different places in Kalman into one central unit that interfaces with master module and different peripherals that we use in Kalman. Every board in Kalman's in Mini-rack standard is a 10 by 10 centimeter PCB that has got few features that are common to each board. So for example, every board has got a DB25 connector, every board has got a CAN transceiver to relay the data between master and that board. And we also integrated a hotspot module to be able to quickly replace those boards even during the Kalman's operation. All of those boards are connected via a backplane that routes signals parallel to each board. And actually, why did we do all of that work to replace all individual modules, all different modules that were doing some job with one standardized system? So our main idea was to again increase modularity and also decrease the setup time that we would otherwise have between each task, between each competition. Also, because we use one common standard between all of our boards, we have definitely less room for any faults to happen. We don't use different buses, we don't use different cables. We only have one standardized connector for everything. And also worth pointing out is that we use Altium Designer feature called templates. And every PCB designer doesn't need to design the PCBs from scratch. They only use the template and later on put all of the additional peripherals of the additional ICs on that PCB board. And on the left, you can see how we what we used before a mini rack system and how mini rack system looks now. So the old system was also rack mounted, but it took definitely more space. And that was because in the past we used normal IP cameras, and those IP cameras required a power over Ethernet switch, they required a Wi-Fi router, and by introducing analog vision system, we're able to remove all of those additional boards and contain the mini rack system in one small box, one small part of the rover, and that's it. After our presentation, you can take a look in our rover and see how much room is there now. We have designed currently 5 different boards in that mini standard, and each of those boards does a different job, does a different role. So we have a master module. It's not fully designed yet, but it will replace the old master module that is not in Meetup system. But for example, we have 2 different boards in Meetup system that do other things. So Analog Max selects what camera the operator sees in a moment, because we have only 2 video transmitters on Kalman, but we can have up to 8 cameras. So a way to multiplex those cameras is to use that board. And also, the drive system has got a different CAN network to be able to be more fault tolerant. So a way to split the main CAN bus between all of those mini-rack boards and the drive system is to use motor/ArmMaster to control them. And now Szymon will tell you a bit more about software solutions in our robot.
Okay, so software is a very broad term which covers the low-level software and the firmware, and also a higher-level one and lots of layers, abstraction layers between, and including ROS. So I would like to focus on the more higher-level software that we are using. The first one is a ground station. It's not the first thing. That if somebody says Mars rover, you don't think about the ground station, but it's very important for us, especially during the competitions when the operators are not able to observe, to see how the rover performs, how the rover behaves. So they only rely on the data that can be presented in our web application and also in other cameras. So that's a very important piece of software for us. I'm sorry, the next one is a manipulator. So manipulator is right now is a 6 degree of freedom manipulator that has implemented inverted kinematics, which drastically improves the way how the operators can control it, and it also is very highly. It's very important feature during the competitions also, and it speeds up the process, the process of completing each task. And there's lots of software here. We're also using robot operating system and Move It and technologies like that to achieve our goal. And yeah, we can see, for example, that the ground station, which is configured for our manipulator, we can see that the operators can, in real time, they have a visualization of real time visualization of our manipulator. And the next topic, which is also very complex, is an autonomous navigation. And the autonomous stack, as Miłosz said before, is installed on our personal computer, on our PC, which is mounted on our Kalman rover. And there are lots of problems related to autonomous navigation because there are lots of solutions of autonomous navigation for planar robots, the robots that are navigating through the flat surfaces like car parks, like magazines and areas like that. But we have to deal with something more complex like Mars terrain. For example, the picture on the left is from your VR challenge, and the pictures above and on the right are from URC. And as you can see, the terrain is very complex and it's very easy to get stuck or to destroy our rover. So we have to take care of our rover, and we have to be sure that it will not be destroyed by its actions. So yeah, the sensors. We have some sensors and we have input data, and we have the very important thing for us is our depth cameras. We have a few real sense cameras which have RGB image and also a depth image, which then is which looks like in the picture on the left. It's just a point cloud with XYZ points. We have also IMU, inertial measuring unit, and sometimes GPS system when the rules ask us to use it. And if we have data, we have to process this data, and we have tested lots of approaches. And yeah, you can see screenshots from RVs, from Gazebo, and robot operating system tools. So we tested it with an autonomous stack that uses that planar robots are used. But for about 1 year, we've trying to create our own way to process this data, to be aware of the slopes of the terrain and lots of obstacles that are present on such a Mars surface. And if you process such data, we receive a map. On the left, you can see just a picture from above from European Roller Challenge, and on the right, we can see different maps that we are able to compute. The one in the middle is informs us if the red points are informing that it's very hard to reach such a point. It's nearly impossible, and the blue ones informs us that it's safe to traverse. We name it the traversability map. And on the right there is also such map, but it's more like it's a binary one. There's only 4 points that are traversable, that we are able to traverse, and ones that we are not able to traverse. And we have a map. We have to do some path planning to find a way for our rover, and if we have a path, we then have to follow this path, and that's it. And with this, it's also worth to mention that we how we test and how we simulate our rover. As I said before, we use robot operating system and gazebo, so that's the first point we want to test our new approach is to test it in gazebo, even if to check if we didn't do anything stupid. The next step is just go outside and ride with our rover, for example, on the playground to check if everything works okay. And the next level was very interesting idea that appeared this year, because we are going to on a competition on ERC. We decided that we can create our own trial ERC trial competition. We've found some judges. We've found people that helped us, and lots of action points has been defined after such competition, and we were able to be prepared for the actual competition much better. And yeah, the final step of testing is the actual competitions. As I said, this picture is from Utah, from the United States, and yeah, that's it, I think. Okay, so thanks for your attention, and if you have any questions, I encourage you to ask. Thank you.
What kind of motors do you have?
It depends. So in the robotic arm, we use, let's say, BLDC motors that are using a custom vector controllers. Those vector controllers are controlled over the CAN FD bus, but in the wheels, we are using just regular DC motors. We are planning to move on to some more, let's say, advanced Maxon motors that I think also would be BLDC type, but that's in front of us.
And how much horsepower does it have?
So unfortunately, the rover is hard limited to 1 meter per second. I think that if we would remove that limitation, the rover would be able to drive up to 2 meters per second, I think.
Okay, yes.
So, something like that. So it's not that slow.
I have a question about how you calculate the map in 3D. You calculate some gradient, and if gradient is higher in some space, then you don't go there. If you would turn back states, how you calculate it?
So you gradient this side, I think.
Yeah.
Okay, so at the input we have a point cloud, which is XYZ point cloud points, and then we try to map this entire point cloud into something called a height map. It looks like that. So you have a point cloud like this. We just create a map of the height, and based on this map, for each group from some of the squares on that map, we try to calculate a surface which is a normal vector which is fitted to these points, and then if we have a normal vector, then we try to represent it as a single number, which informs us what is the angle of this normal vector, and then as a result we get something like this. So this is a crater like this, I think. Yeah, that's the same simulation. That's the same situation, and you can see that these points are higher because they're lighter, and in this case we can see that the angle of the surface is much harder to traverse. I think that I expected. Okay.
So where the exact calculation is done in this application in the station, or for example in the competition when you have a terrain in front of you, you need to select the proper path or something?
We are not able. It would be hard to send all this data over RF and then send it back. So it's on a rover. There is a PC on the rover and it calculates everything on the
What
rover.
class of computation systems?
x86.
Okay.
Like i5 with 16 gigabytes of RAM, I think.
Okay.
When you're collecting this data, what sensor are you using? It's not visual, right?
It's Intel Resense.
From the camera. From the camera that
They have it on the
collects
slide.
RGB data and depth data.
It's okay. It's visual then.
Yeah.
It's not infrared or.
It's infrared.
It's infrared.
Yeah.
Okay.
There are four cameras, the four eyes you can see. The first one is yeah.
So the LiDAR is used for the obstacle avoidance only, or
We don't have any LiDAR on our.
any LiDAR?
No, we only have
So this is just okay.
we only have recent cameras.
Okay.
So essentially, you are not doing everything in 3D. You are just projecting everything
Yeah.
to 2D.
Yeah, we do something like that. But we can also but we still see lots of ways to improve this technique because I think in this area always there's something to improve, and we are also thinking about the fully 3D
So
navigation.
is it the case that it's generally adding one more dimension would be much more complicated for your purposes, or is it that there is no ready tools and no ready solutions for the sensors that you got?
We have some problems with 3D solutions, and we've tried with this 2D approach, but I don't think that it's impossible. We are just experimenting with it right now.
Also, navigation in 3D space is still like an open problem to solve. So 2D is much easier to solve, and just simplify the space and put way simpler algorithms that also don't have to include the dynamics of a system.
You have mentioned that there are lots of custom parts in the rover. How often it breaks?
So custom parts of the rover.
That you make a lot of parts, mechanical parts, electronic parts, to software, and it makes me wonder how often you need to repair it.
Okay.
So I would say all the time. But it really depends. If we do a lot of maintenance, especially before the competition, we don't have a lot of work to do in terms of parts that are breaking. But for example, when we were getting out of the car and setting the rover before getting there, we encountered an issue that second degree of freedom in our manipulator by itself moves down. Just moves constantly a bit down. And for example, it's the current issue that we are facing. But I would say that we have constant room for improvement. But after those 5 years, a lot of the issues that we have been occurring a long time in past are not present nowadays.
Okay. What's the payload of your manipulator?
Once again?
Payload. What's the payload?
So the way that we can.
Yeah, exactly.
It depends on the So our manipulator can be extended, I think, up to 1.5 meter, but it's designed to be able to lift up to, I think, 10, 15?
5 or 10, something like that.
Yes, so safely up to 10 kilograms.
Quite impossible.
But if you don't extend the arm all the way forward, you can even lift the entire rover by the arm.
Wow. Oh.
And we can showcase it in a little while.
So we can.
Okay. So thank you very much for all those questions. Thank you.
Okay, so thank you guys for this awesome presentation. And now, as we have some lack of time, so now we will go to the next presentation that will company Astor will present the educational robot Astor, and then we'll make a break, beer break party or something like that. So sorry for not having a break now. Or maybe we can have a 5-minute break because they will set up. So yeah, so go for a short break, and we'll meet at